Okay, here we're going to here in equilibrium, slide 24. They're put together because they have very similar receptors. They're called hair cells, and their transduction event is very similar. Okay, nature of sound. Sound comes to as waves of compression and rarefaction of air molecules, and the distance between one peak and another one is the frequency, and that's pitch. And then there's loudness, and loudness is measured in a scale, a logarithmic scale called decibels. Everybody's heard about how many decibels something, um, uh, how loud something is. Okay, ear anatomy. We have to look at really outer ear, which is really just your pinna, and then what's called the external auditory meatus, and then the middle ear. We get to the eardrum, which is called the tympanic membrane. There's a eustachian tube, or also called auditory tube, that connects your middle ear to your nasopharynx, and that's to equilibrate pressure across the eardrum. And then there's the smallest bones in your body, the middle ear ossicles, the malleus, the incus, and the stapes. Uh, and they're also known as the hammer, the anvil, and the stirrups because they look like those things. And the malleus incus actually evolved from reptilian jawbones. It's really unusual. We have one. This is more evolutionary history. We have one jawbone, a mandible. Reptiles had three, and two of them migrated back into the middle ear and became the mammalian malleus and incus. Okay. Or forget about the tensor tympani and stapedius muscles. These are muscles that actually stabilize the ossicles when a really loud noise enters your ears. We'll talk about that reflex a little bit later. Then we get to the inner ear, the bony and membranous labyrinth. And the cochlea is where the auditory receptors are actually located in the cochlea. It's spiral shaped and it has three spaces: the scalum tympani, the scala vestibuli, and the cochlear duct. And the cochlear duct is filled with a fluid called endolymph, and the scala tympani and the vestibuli are filled with a fluid called paralymph. And the spiral organ is where or also known as the organ of Corti, is where the hair receptors, the auditory receptors are located. Hair cells and supporter cells with the stereocilia. And then we're going to talk about a couple of important membranes called the basilar membrane and tectorial membrane. Here's a cross section through our ears, and here's the outer ear, the external ear, the auricle or pinna, the external auditory meatus is what your ear canal is called, and then tympanic membrane right here. And then on the other side of the tympanic membrane, here is the middle ear with the three middle ear ossicles that connect the tympanic membrane to something called the oval window, which is over here. And then what is the oval window? Right there, underneath the stapes. And then this is the auditory tube, also called the eustachian tube, that goes to the nasopharynx. And that's what allows you to stabilize the pressure on both sides of the tympanic membrane. If you go up real fast or down real fast, the pressure will change on either side, and that's why you open your mouth to chew your gum to equilibrate the pressure on both sides of the tympanic membrane. It happens a lot when you go into airplane flights too. And then over here is the inner ear, and the three semicircular canals. That's going to be for equilibrium. And here is the cochlea, the spiral cochlea, and in there is where the auditory receptors are located. And here's the nerves leading the vestibulocochlear nerve leading into the brain. So I have to look at the physiology of hearing, the function of middle ear ossicles. What do they do actually? Well, they essentially amplify the waves, and this is because we're talking out here in a very thin medium, causing these waves in a thin medium. But these waves in a thin medium uh, have to be conducted to waves of a thick medium, the paralymph in the vala tympanic inside the cochlea. So we really um, have to amplify those waves, and it's amplified but because the size of the oval window compared to the size of the tympanic membrane. The membrane is quite large, and it moves the middle ossicles when you hear something, and this moves the stapes, and it's amplified because the oval window is much smaller than the tympanic membrane. You have tympanic reflex, and this is if if a really loud noise enters your ears, these muscles, trapezius, the muscles inside the middle ear will actually tighten and stabilize the ossicles so they won't move too much, so they won't cause damage to our hair cells. Okay, here we're going to talk about the stimulation of the cochlear hair cells. How do these waves get conducted to the hair cells, um, and then how the hair cells actually work. Um, First, the vibration, the paralymph caused by the stapes moving the oval window. Um, those waves go down down the vala scala vestibuli, and there's a vestibular membrane that lines this, and this is going to cause waves from the paralymph into the endolymph, and this is going to cause movement of something called the basilar membrane. Um, and stereocilia are embedded in this tectorial membrane that doesn't move. And the bending of these stereocilia that are in the membrane of the hair cell uh, causes opening of potassium channels that lead to depolarization of hair cells that leads to action potentials in the sensory neuron. And I'm going to show you how that all works in the next couple of slides. Oh, I'm not calling out the slide numbers anymore. 28. This is 28. And here's a cross section of the cochlea. And you can see these chambers, the scala vestibuli, the scala tympani, and the cochlear duct here. These have paralymph. This has endolymph. Endolymph is a really strange liquid. We'll talk about that in a little bit. Anyway, and here's this basilar membrane that the organ of Corti is on. This is the spiral organ of Corti, and these are the hair cells right here. And they have stereocilia, and those stereocilia are embedded into a tectorial membrane, which doesn't move. And here's an actual microscope view of the spiral organ. And what's going to happen is movement in the endolymph is going to cause movement in the basilar membrane, and these stereocilia and these hair cells are going to move with respect to the stereocilia that are stuck in the tectorial membrane, and this is going to distort the membrane and cause a receptor potential to be generated. So these are so hair cells, autoreceptors are really mechanoreceptors.